What I'd like to tell you about is some work that we did earlier this year. That's part of a long-standing program that goes back a couple of papers all the way down to 2010 with some wonderful collaborators, including Roberto Mello-Koch and Yolanda Lozano, and Michael Abbott, who's a postdoc at the University of Cape Town, Andrea Princeton, a former PhD student who's now a postdoc at Surrey, and Nitin Raghunath. So if we pay much attention to the words that have been going around in this meeting, I think it's fair to say that in as much as we can reach consensus in this community, we're in consensus that space-time in some sense is emergent. It doesn't seem to be fundamental in the sense that it doesn't seem to be some stage that everything else happens on. So this work is largely motivated by one question, and that's to try and understand how space-time emerges. So in the sense, it's a little different from the flavor of the talks in the rest of the meeting, in the sense that we're going to do very little, small little things, but that result in some cute mathematics and lots of pretty pictures. So I hope it compensates. So the question is, how does space-time emerge? And I mean this in a very specific sense. How does space-time emerge in the context of the type 2b ADS4, type 2b ADS5 cross S5 n equals 4 super Yang-Mills duality. So the duality tells us that a theory of gravity is related to a theory of matrices interacting on a flat background. Somehow those matrices in the matrix model need to code the geometric and topological properties, space-time properties of the gravity theory. So we're going to be interested in asking specific questions of the gauge theory to see how space-time is coded. So the gauge gravity duality, as realized in the ADS-CFT correspondence, is a marvelous tool that we've heard lots about during this conference, and it comes. One of the nicest things about it is that it comes with a built-in dictionary that tells us how to relate various things on either side of the correspondence. On the one side, on the gauge theory side, we have a matrix model. We have Yang-Mills theory. It's got a bunch of matrices on there, and I build gauge invariant operators out of these matrices. So I know that if I take operators with order 1 matrices, they have R charge of order 1, and we can organize everything according to their R charge, according to how heavy these fields are, these operators are. Order 1 R-charged operators correspond to supergravitons in the gravity theory. And then Berenstein, Moldesina, and Nastasi came along and told us that when we're looking at operators built of scalars of order root n, where n is the gauge, the rank of the gauge group, then we're talking about strings. And we saw for the first time in the BMN PP wave correspondence that we could start to really probe the stringiness of string theory. If we go up to heavier operators of order n, correspond to membrane-like objects, D-branes, and we'll be interested in a very specific class of D-branes, so-called giant gravitons on these backgrounds. And then in a beautiful paper, Lin, Lunin, and Moldesina showed us not only how to classify all half BPS geometries, they also told us that if we look at operators of order n squared, then these things are heavy enough that they back react completely and they give us whole new geometries. So we should really ask how the properties of these geometries, how these new geometries are coded in the gauge theory. This is a difficult question to ask, so it's worth starting small and asking very specific questions about very specific sectors of the Yang-Mills theory. So one of the best labs that I know of that we can ask and answer these questions is by looking at giant gravitons. Giant gravitons are in type 2b string theory. Giant gravitons were discovered by McGreevy and Susskind and Tubas in 2000. And they're D3 branes wrapping some 3-sphere in ADS5 cross S5 and moving along some great circle on the 5-sphere. They're tensionful objects, they're extended, so they have a natural inclination to contract and reduce their tension, but they're stabilized classically through coupling through to the RR5 form flux in the supergravity background. They admit a microscopic description as a large number of coincident gravitons that couple to some background Ramond-Ramond potential, and that polarized by the Myers effect into an extended DP brane. That's the D3 brane that wraps the 3-sphere in ADS5 cross S5. In fact, there are 2 3-spheres in ADS5 cross S5. There's one of a bounded size in the S5, and there's one that's unbounded size in the ADS5, and they can wrap either one of them, and that gives you a giant graviton, or what is known as the dual giant graviton. And they have distinct properties, and these properties need to be realized in the gauge theory. And in the gauge theory, initially in Susskind and McGreevy and Timbas's paper, they conjectured that these would be dual to single trace operators made up of these gauge fields, because, well, that seemed like the obvious thing to realize the space-time uncertainty principle. But then in a later work, Balasubramanian and Strassler and collaborators came along and said that, well, actually these single trace operators didn't satisfy all these properties when they got large enough as they would need to be to describe these membranes. And they conjectured that another gauge invariant operator that you could make was in fact a determinant-like operator. And in fact, the determinant would describe the maximal size giant on the 3-sphere in S5. And if you went to smaller size, then it would be some kind of subdeterminant operator. And they showed how you could resum traces in very much like one of the slides that Rob had up. You could resum all these traces into a determinant-like thing, and that would be the determinant. Oh, sorry, that would be the determinant-like operator that would correspond to giant gravitons. And then in the same year, Corley, Javitsky, and Ramgulam came along and said, well, actually, the determinant and subdeterminant-like operators are a special class of a set of polynomial-like operators called Schur polynomials that were built out of the complex Higgses in the Yang-Mills theory. So this was related to the characters of the symmetric, the characters of Sn. And this guy on the left-hand side was the Schur polynomial built out of out of one of the 3 complex Higgses in Yang-Mills theory, let's say Z. The Schur polynomials are labeled by some representation, which you can think of as a Young diagram with n boxes. In the completely antisymmetric representation, where this Young diagram is just a column of n boxes, n can only grow as large as capital N. And that was what coded the space-time uncertainty principle, and this Schur polynomial became effectively a determinant-like operator. So it all fitted in quite nicely. And there were more things that you could do with these Schur polynomials, like, for example, they satisfy a nice product rule where if you take a Schur polynomial in representation R, multiply it by 1 in representation S, then you can write it as a linear combination of Schurs in some other representation T. And these coefficients in this linear combination you can calculate from the from the Littlewood-Richardson rules for basically combining Young diagrams. So this was very nice, and this follows from the Schur-Weil duality, and it allows you to calculate endpoint correlators of these guys. So that's a really pretty piece of technology that has begun to emerge over the last couple of years. But the question that we wanted to ask was how the shape of the D-branes in the gravity side of the picture was coded in these Young diagrams, in these Schur polynomials, which are, after all, just polynomials made up of matrices that you're taking a trace over at the end of the day. So how does this thing code the shape of the D-brane? So we know, for example, you know, as a toy problem, we know that. Well, not entirely trivial toy problem, but we know that if you take the three-sphere, so it's a round three-sphere, and the giant graviton is the D3 brane wrapping this three-sphere in, and I'll talk just about the S5 now, then it's a compact object. And a compact object needs to satisfy Gauss's law, and Gauss's law says that you can't put lone sinks or sources on such a compact surface. So for example, well, in string theory, this means that you can't attach a lone string, one endpoint of a string, to such a compact surface. So for example, if we consider two such giant gravitons, just as a cartoon of this story, then a configuration like this, where I attach a single string to this surface, is not allowed. But one like this, where a source is matched by a sink, is allowed. If I have two such surfaces, attaching one open string between this giant and this giant is not allowed, unless I match it by an oppositely oriented string joining these two. Right. So that's Gauss's law. And this needs to be realized in the gauge theory. And how it's realized in the gauge theory is a beautiful picture that was started with Balasubramanian et al. In 2002, and then continued and elaborated on by Robert de Mello-Koch's group in a series of papers that's tour de force and representation theory. But ultimately, it boils down to the following. In the gauge theory, a Schur polynomial describes the giant graviton. If you want to attach strings to the giant graviton, then you need to pull off z's from the Schur polynomial and replace them with words that correspond to the string, and organize them in such a way that the boundary conditions are appropriate, that you can pin them to the string. So if I start off with a Schur polynomial just made up of z's, I pull off some of these z's and I replace them with words, let's say w, and then I trace over these guys, and I properly account for it by tracing over this subduced representation. Then I can produce something that is dual to an excited giant graviton, or a giant graviton D-brane with strings attached. So you then count the number of such operators that can be constructed for a given representation, and you find that it matches exactly the allowed states, the states that are allowed by Gauss's law in the gauge theory. So in this way, you can see Gauss's law coded in these operators in the gauge theory. Right? But in some sense, this is kind of trivial. Right? It's not really trivial. If you'd like, you're welcome to go have a look at the papers. But it's not a trivial calculation to show at all. But from the point of view of the topology, I have a compact surface, and any compact surface needs to satisfy Gauss's law. So I'm not distinguishing between a sphere or a torus or something more complicated. So what we wanted to understand is if we could find some way of distinguishing between different genera, for example, if there was some way of coding the genus of these objects in the gauge theory, and how we could understand these things. And this was largely motivated by a nice paper by Nishioka and Takeyanagi that appeared in 2009 in a slightly different context, not ADS5, not the ADS5 CFT4 correspondence, but the ADS4 CFT3 or ABJM. Or ADS4 ABJM correspondence, where they found toroidal giant gravitons, which weren't really found in the ADS5 context before. And then Berenstein and Park, in a follow-up to this, tried to understand these the operators that would be dual to this. The problem, though, is that, at least the way we were thinking about this, constructing Schur polynomials in ABJM are a much more difficult problem. So we tried for a little bit and got stuck for a little bit, and then decided to go back to ADS5 and try and understand the problem in that context. Right. So fortunately for us, at the turn of the century, Andrei Mikhailov wrote down a beautiful construction of giant gravitons algebraically, and they're realized as follows. Any holomorphic function defines a supersymmetric D3 brane in R cross S5 as an intersection of that function f equals 0 with the 5 sphere in this way. The amount of supersymmetry that these solutions preserve depends really on how many arguments are in the function. If there's just a Z1, then it's half BPS, Z1 and Z2, a quarter BPS, Z1, Z2, and Z3, 1/8 BPS. So for example, let's call this example 100. The usual sphere giant that we were talking about just now corresponds to a linear polynomial, Z1 minus alpha equals 0. This fixes Z1 in terms of alpha. And then I can write down Z2 and Z3 in terms of Z1 like this. And this is clearly a 3-sphere with the radius 1 minus square root of 1 minus alpha squared. So the maximal giant, the giant that's the biggest size it can be in this sphere, corresponds to alpha equals 0. So I call this 100, labels polynomial 100, because it has one Z1, no Z2, and no Z3s. I can extend this to the case M00, and this corresponds to a holomorphic function with multiple zeros, and this leads to multiple concentric giants. So what we did was try and understand what happens if you add to this function f of z1 some meromorphic function of z2. So some function of z2 that just has poles in it. And a simple example of that would be this 110 polynomial, which has one z1, one z2 that enters in this form. So when epsilon is 0, this is back to the sphere giant. When epsilon is non-zero, we have some residue on the z2 plane. The spatial part of the D3 brane world volume is parameterized by phi 3, which is the argument of the complex z3. And some portion of the z2 plane, all other aspects of it being fixed by f of z1, z2 equals 0, and the sphere condition. So the domain in the z2 plane that corresponds to the solution is D, that satisfies this problem, this property. This bracket should be outside there. So you can see if epsilon is 0, then D is really just the disk mod z2 squared less than equal to 1, which brings us back to the sphere giant. So that's a sort of a reality check. When you turn on epsilon and you have a non-vanishing residue on the z2 plane, you puncture the disk, and you can read off the topology of this thing directly from that puncture. And it works like this. When epsilon is between 0 and some critical value, the critical value lying when this piece pinches off like this, then the topology of the spatial topology of the giant graviton is an S2 cross S1. The S1 part corresponding to this C1 cycle here, and the S2 part corresponding to the phi 3 circle fibration over this interval C2 here, where the circle goes to 0 on each end. Right, so that's an S2 cross an S3, and when you go past this pinching point, then it's topologically an S3, but a geometrically deformed S3, not a round sphere anymore. So you can then generalize this and add a couple more Z2s into the picture like this. Now the function is still a 110 polynomial, except it's got higher order poles, no longer simple poles. And the geometry is, the topology is the same. It's also an S2 cross S1, but the system has a n-fold symmetry under Z2 going to e to the I2 pi over n Z2. So for example, when n equals 5, this is the picture, and you can see that past a certain critical point, this thing degenerates into into a disjoint union of 5 3-spheres, but it's an S1 cross S2 with epsilon like that. The next thing we tried to do was basically pull apart these poles and consider separated poles in the Z2 plane. When you do that, what you find is that the topology of the giant graviton is an n-connected sum of S2 cross S1s that you can work out like this. So for example, if you take the 130 case with simple poles on the Z2 plane, cuts across this domain D like this will separate out these poles into three parts, each of which will be an isolated single pole, each of which will be an isolated simple pole, and that's an S2 cross an S1. And then you glue them back together again by a connected sum, so that's a 3-connected sum, S2 cross S1 connected with S2 cross S1 connected with S2 cross S1. Increasing the residues, as we did in the previous case, is more complicated in this case, but still you get this degeneration into disconnected spheres. and this was what we call the 130 case. And a useful check of this is that the topology of these D-branes don't care what you label as Z2 and Z1. So the 130 case should be the same as the 310 case. The simplest polynomial of that form looks like this. And here, the area of the Z2 plane, of the Z2 plane that's occupied by the solution D is a three-sheeted Riemann surface like this. And to work out what the topology of this thing is, it's got branch cuts that go from 0 to some point inside this white region here, which you can cut along the branch lines. And each of those sheets corresponds to a single puncture of these sheets, which you then glue together. And again, it matches to the the three connected sum S2 cross S1. Good. Just by way of reminder, the connected sum of three manifolds, let's say M and M, is formed by joining a point on M to a point on N with a tube that's an S2 cross some interval, which is the same as an S3 with two punctures. So in one dimension lower, this is kind of what the connected sum looks like. And this is what it will look like for the three manifolds. And then connecting a tube between any 2 points on the same manifold just adds an S2 cross S1. So M plus this tube is the same as connected sum, connecting M with an S2 cross an S1. And one dimension lower, this is kind of what it looks like. So the topology started becoming more and more complicated in this case, and we needed to invent some notation to handle this. In particular, we didn't want to be cutting and gluing Riemann surfaces all the time. So if we define an S3 to be this little block here, and an S2 cross an S1 is the little block with a hole in it, and a tube, S2 cross an interval, as something like this, then we can take this problem and boil it down to constructing these little tinker toys with these cubes and tubes. So this is a play on Grothendieck's Descente d'enfant. So for example, and a trivial example, if I take two S3s and I connect them together, I get an S3. This is nothing but the statement that the three-sphere is the identity for prime factorization, which is really what we're talking about here, prime factorization of three manifolds. Adding a handle to this makes it adds an S2 cross S1, just as we had up here in our picture language. This is what it looks like now. And a slightly less trivial example is the 220 polynomial, like that. The old way would involve solving for Z1 in terms of Z2, writing down this the two-sheeted Riemann surface, connecting them up together, cutting, gluing, and then reading off from this what the topology was. The new way, using prime factorization, because let's face it, it doesn't really matter what connection you're talking about, primes are awesome. This one being Optimus Prime. Yeah, I have kids, sorry. So, for example, the 220 case would look like this, an S2 cross S1, S2 cross S1, S2 cross S1, S2 cross S1, glued together by these tubes. And then you just count the number of tubes, add 1 for the handle, and that tells you that this is a 5-connected S2 cross S1. That's as easy as it is. So we're able to give a general construction then for the Mn0 polynomial with higher order poles, where if little n is the number of poles in Z2, little m is the number of poles in Z1 with total order n and m, you draw a grid of m by n S2 cross S1s, connect them all with in this lattice with m vertical tubes and n horizontal tubes, and then count the number of horizontal and vertical connections, add 1, and that'll give you the topology of this. So as a worked example, there's a 330 case. Here k is 16, so this is 13, so this is 13 connected S2 cross S1s. Going from here to here, we collapse 2 of the poles, and from here to here, so this in the poles in the Z2 plane. From here to here, we collapse 2 of the poles in the Z1 plane. In all cases, the counting is fairly straightforward now. We then moved on to the 1/8 BPS case, where things are a little more difficult. Well, generically, they're much more difficult, but we were able to treat at least the case M and M, so an equal number of Z1s and Z3s, and the polynomials, the holomorphic functions that we were talking about, look like this. Again, you can get a counting of the topology. In this case, it's an S1 cross some connected sums of tori, where we were able to give a counting of what that k is in that case. Good. So then, by way of conclusions, the takeaway statement here is that if g of z1 and z2 is some meromorphic function with a number of poles, with some number of poles in the z1 in z1 and z2 counted by m with total order capital M and n with total order capital N in z1 and z2 planes respectively, the quarter BPS giant graviton in ADS 5 cross S5 is given by a meromorphic function like this, and it has a topology given by a prime decomposition of the three manifolds where k, the connection of the connected sum, is counted like this. So this gives us a number that we can go and then try and calculate in the gauge theory. So what we've done is set up the problem in the gauge theory, set up the problem in the gravity side, and that leaves us with a number of questions to address. The first of which is how to systematically treat the 1/8 BPS giant sector, and then, of course, trying to understand what the operators that are dual to these giant gravitons and how these topologies are coded in those operators is an open problem, as well as the classification, a similar classification for the giant gravitons in the ADS4 CFT3 correspondence. Thank you.